This video will explore the effect of CFCs on the ozone layer. The background information required will be reviewed first, such as what ozone is, where it is, and how it's made, why there is good and bad ozone, not directly related but presents another issue, as well as what CFCs are and how they're made. Ozone is formed through the photodissociation of oxygen gas in the atmosphere by UV and higher energy radiation, which is able to break the diatomic molecule's double bond as seen in the given equation. Because E equals h nu, Planck's constant, times frequency, h nu in a photochemical reaction simply means the energy from a photon provided by the sun's radiation. In the first equation of the given reaction mechanism, note that the atomic oxygen is provided by the equation from the last slide, which showed the photodissociation of oxygen. The equation is reversible because while the collision of atomic oxygen and oxygen makes ozone, ozone will always decompose or be photodissociated. The initial ozone created has excess energy and is therefore unstable, so it transfers away its energy by colliding with other molecules in air. The parentheses in the third equation denotes excess energy and X as any other atmospheric molecule. So that's how ozone is formed. But why is it good? The given equation shows the benefit of ozone, because it protects us from the sun's radiation in the stratosphere by absorbing the energy and dissociating back to atomic oxygen and oxygen gas. Notice how the products are the same as the reactants for the reaction mechanism from the last slide, creating a cycle of ozone formation and photodissociation. But ozone isn't all good. In the troposphere, it contributes to photochemical smog. Ozone is very reactive and toxic, and it will adversely affect sensitive people like those with asthma, as well as the elderly and young. Tropospheric ozone can be produced in many ways with different molecules. One example is through nitric oxide, which is produced in internal combustion engines. Higher temperatures such as those in engines will produce more nitric oxide. Using Le Chatelier's principle for this endothermic reaction, equilibrium will shift right. Because nitrogen and oxygen gas are found in the atmosphere, any high temperature will produce some nitric oxide, like in power plants as well. Nitric oxide produces ozone through the reaction mechanism shown. First, it is oxidized in air. The resulting nitrogen oxide is then photodissociated to nitric The resulting nitrogen dioxide is then photodissociated to nitrogen oxide and atomic oxygen. The atomic oxygen, as previously explained in the formation of ozone, combines with oxygen gas to make ozone. Now, CFCs. CFCs, short for chlorofluorocarbons, molecules with chlorine, fluorine, and carbon, were once widely used as refrigerants and aerosol propellants. Back in the 70s, a huge ozone hole over Antarctica was discovered. Because of that alarming finding, the next decade saw an anti-CFC push, culminating with the Montreal Protocol in the 90s, which ended the use of CFCs. It was good that CFCs were quickly phased out, as ozone depletion leads to genuine concerns about the health of all life on Earth. Greater UV radiation would reach the Earth's surface, increasing our risk of skin cancer due to how radiation can damage organismal DNA and create mutations. We must keep in mind that the Antarctic hole is a misnomer. Ozone isn't completely absent over the continent, but just much thinner than other places around the globe. This doesn't mean it's not a problem, though. However, focusing on the Antarctic hole only is also bad because ozone is being depleted everywhere. It just so happened that Antarctica bore the brunt of the CFC damage. That is the effect of CFCs on the ozone layer. But exactly how do CFCs degrade ozone? We must examine the structure as well as the process of its production to truly know. CFCs and HCFCs are normally produced by exchanging the halogens of the reactants, such as chlorinated methane and ethane. The given reaction shows the creation of an HCFC from chloroform. There are many different combinations of CFCs, such as CCl3F or CCl2F2, and the closely related HCFCs, which are used for similar purposes and similarly affect ozone. But how are hydrocarbons chlorinated in the first place? Chlorohydrocarbons, or organochlorides, are themselves produced through multiple methods, two of which I will explain. The simplest method is collision with chlorine gas under UV light to ensure the separation of diatomic chlorine so that free chlorine atoms can bond with the hydrocarbon. An example reaction is given using methane. This process is often difficult to control and repeated with the product for subsequent replacement of hydrogen with chlorine. The equation given will eventually yield chloroform, which is one chemical used to make CFCs. Another method reacts gaseous hydrogen chloride, which is hydrochloric acid when aqueous, with a hydrocarbon. An example uses ethylene or ethene to produce a chlorinated ethane, which can also be used to make CFCs, as seen in the second reaction. The problem. The chlorine in CFCs is photodissociated in the stratosphere as seen in the first reaction. Because the C-Cl bond is more easily broken than the CF bond, remember bonding distances? We have free Cl in the atmosphere from CFCs, not free fluorine. Now with free chlorine atoms in the air, a terrible reaction mechanism occurs. The chlorine from CFCs breaks down ozone. The first step of the reaction mechanism has a rate law R equals a constant times the concentration of chlorine times the concentration of ozone. This is experimentally determined. You cannot use coefficients to find the rate law. To make matters worse, the resulting ClO is not inert. It photodissociates into Cl and O, and the chlorine is allowed to break down more ozone. When both sides of each mechanism are added and cancelled, we are left with a simple final equation. Notice how chlorine itself is merely an intermediate and not used up. It is therefore a catalyst, and the rate law with chlorine for the first reaction in the mechanism increases with more chlorine. More chlorine from CFCs therefore accelerates the decomposition of ozone. The situation is much better today. The ozone hole has stabilized. In fact, its area has begun to decrease as CFCs were replaced by HFCs. However, CFCs last a long time in the atmosphere and will continue to damage the ozone layer, slowing the closing of the ozone hole. While HFCs degrade faster than CFCs, HFCs are still a greenhouse gas like CFCs. We did well to quickly meet an environmental challenge by phasing out CFCs. The question is, can we do the same to combat carbon emissions and climate change in general?